thermochemistry includes the last items on this set of learning objectives, specifically a somewhat short conversation about how Hess's law is used to determine values of enthalpy, specifically enthalpy changes for reactions. Hess's law is a relationship that tells us that overall enthalpy change, delta H, for a process, a reaction, would be the sum of the enthalpy changes for individual steps in the reaction. The reason this is feasible is because enthalpy changes are state functions. The initial and the final states are really all that are necessary. The overall change is going to be the same regardless of how many steps it takes to get to a product or through the process. An example of how this can be used is with the Haber process, trying to use that to understand how to calculate the enthalpy change for the formation of hydrazine. N2H4 is hydrazine from hydrogen and nitrogen. It turns out to be something that's difficult to calculate, and so the use of Hess's law and knowing about this other reaction, including hydrogen and nitrogen to make ammonia, gives us a means to calculate the enthalpy change for something that's inconvenient or not very feasible or practical to do. So what we'll do is we'll find in a table of values someplace, and there's places to look these up. No one knows these numbers automatically, of course. The heat change required or associated with the reaction of hydrazine N2H4 to make ammonia by adding some hydrogen. So this is hydrazine. And if you have the information available to you that tells you that the heat for that reaction is provided, it's exothermic, 187.6 kilojoules released, then the process that we're looking for to understand the formation of ammonia in this is another one. Sorry, the one we're looking for is making hydrazine, but you can use the formation of ammonia, the third one, in combination with the other two to come up with the unknown change in enthalpy. The heat of the two processes will add together to, that we see here, to give us the heat of the last step. So, and if you add reaction 1 to reaction 2, you add those enthalpy changes together, should add up to the value, and this is a known value, for the formation of ammonia. So if you think about it, reaction 1 plus reaction 2, what is the net happening? In other words, there's hydrazine on a reactant and the product side, and therefore what remains is what you see in the last line. 3 hydrogens, because there's 2 from the first reactions and 1 from the second, plus nitrogen combines to make 2 ammonia. And that delta H value is provided elsewhere. So how does that all work together, and why does this make sense? In other words, the combination of those first 2 heat changes gives us the overall process of making ammonia in the net. But the inference then is that you can take the sum of the 2 at the bottom there, and the difference between delta H1 and delta H2 is the one that we're missing. So look at it this way. The sum for the reaction overall was reaction number 1 that we are trying to find is going to be delta, the first one plus the second one gives you the heat of the reaction overall. And so you can take delta H1, you can find that by subtracting delta H2 from the heat of the first reaction. And so the first one was known. It was 92.2 kilojoules released. The 92.2, and the other heat of reaction was known to be 187. And so if you look at it in terms of these arrows, the first reaction was nitrogen plus hydrogen to make hydrazine. And the second reaction had to do with hydrazine plus hydrogen to make ammonia. The third reaction, the overall process, was the net of these 2. So the sum of their enthalpy changes gives us this enthalpy change for the one that we want to know, or relates to the sum of the one we want to find. Now, let's use this for another example, and that will hopefully make it more clear. All right, so here's a multiple choice question so you'll know if you're getting it right. Here is a caution. These problems can be complicated in terms of the arithmetic. One has to be extremely cautious to write things out, not to make mistakes. I can vouch for the fact that I am as able to make mistakes as anyone else is, because it's so easy to try to feel like you're going to make a shortcut someplace, and if you skip a step, you just totally don't know what you've missed. All right, so if we're going to look for the heat change for the process of propane reacting with water to make carbon dioxide and hydrogen, not that we know how that would happen, we don't care, we could calculate the reaction enthalpy if we know of some other information. First of all, you can find out from some chart someplace that propane in a table, propane reacting with water can make carbon monoxide and have hydrogen left over. And you can also find somewhere else carbon monoxide reacting with hydrogen can make CO2 and hydrogen left over. And those each have values for delta H that you can look up because you can find them. We don't have to guess anywhere. But how can you use these together with Hess's law to come up with the overall process of propane with water to make CO2 instead of carbon monoxide, the way it's shown in that first reaction? So reaction 1 that I've marked here now can be left the way it is because we want 1 mole of propane, and the 3 moles of water is half of what we're going to need. It's not the whole thing. And so let's see what else we're going to have to do. We're going to have to do something to reaction number 2. Reaction number 2 then can't be used as is. We're going to change the moles to make it add up to the total process at the top. Well, if you're paying attention here, we're going to need this to be 3 times as many moles of CO2. And if so, everything in that reaction gets multiplied by 3. So put 3 on the carbon monoxide, 3 on water, 3 on hydrogen also, and then we'll have to multiply delta H times 3. And guess what? That one's not a hard number to do. 3 times 41 would be minus 123 kilojoules. Again, these are always per mole. This first one is per mole as shown in the reaction, and so multiplying by 3 gives us minus 123. Now, if you take reaction 1 as shown, plus reaction 2 with the multipliers included, what do we have as a net process? So it looks to me like we should have C3H8, so far so good. And now we have not just 3, but 6 water molecules, so far so good. By the way, I'm quitting to write the phases because everything is gases here. What phase things are in is important, but as long as nothing's changing phases in this example, we're safe. Now we have to figure out what else is on the reactant side that to be included. Well, there's carbon monoxide on the second reaction, and there's carbon monoxide on the first reaction, but on the product side. So this will cancel out of our net reaction. We don't have to include it. Then the product side, we're going to have hydrogen in 2 places. Hydrogen in the first reaction, hydrogen in the second reaction adds up to a total of 10 hydrogen. So far so good. We wanted that to look that way. And then we also have the 3 carbon dioxide from reaction 2. So those 2 processes, the way we've stacked them up and putting a multiplier in the second one, give us a net process for which the delta H, sum of these 2 processes, should give us the one that we want to know, the heat of the reaction for the propane with water to make CO2. So that means we're going to take it how? So delta H is going to be 499 minus 123. And if we're going to do our math successfully, get out your calculator. Looks to me like it should be 376 kilojoules. So answer A. Having multiple choice helps you to know if you've gone in the right direction. Otherwise, these are just numerical problems, and you can never know when you've made a mistake until you've not verified that your answer is present. All right, this is simple examples with Hess's law, and I wanted to just start with simple examples. Hess's law is going to be used in the remaining sets of calculations that this chapter includes. So this is just a method of how we sum individual processes to make an overall process and use the heats of each reaction combined to come up with an overall enthalpy change. These take practice, and so be very, very cautious about writing out all the steps And be very careful with your math. Watch the signs. Pluses and minuses are going to be important. If you get them wrong, your answers are going to be completely weird. So there's a lot of places, a lot of pitfalls. You've got to be very cautious. Use caution. Caution advised for most success. All right, good luck with these. I hope they help you on your homework. Please ask more questions, and I'll see you in class.